Okay, good evening, everyone. So I'll be speaking about the goals and abilities of DFT, running a VASP job, preparing VASP input files, checking for the output data, and visualization of the CHEM orbitals. So I would like to point that I wouldn't delve too much into the calculations. I mean, how to run most of these things because I feel like most of us are familiar with it. I would be speaking more about some things that I found out, correlating the theories that we learned in class with like the practical. So first of all, the density functional theory is used to calculate the electronic structure of atoms, molecules, and solid, which in turn helps us to like understand material properties using functionals, which is function of a function. Now, in classical physics, the basis is like the Newton's equation, but in quantum mechanics, it's like the Schrodinger equation. Now, the Schrodinger equation only helps us to understand a one electron body system. But now, what the DFT is helping us to do is to approximate the Schrodinger equation for a many body system. If we remember very well, Dr. Killian tried to like explain a many body system from one electrode system, and we also try to go from a many body system back to one electron system. So DFT helps us to figure out total energy of a system using electron density, which is function of position. The DFT helps us to uses orbitals and not wave equation. It gives an insight into relating density to ground state properties. Now, we know that like the ground state properties of molecules are important because at some points you have to go to like the excited states. So like the ground state properties are like very, very important, and the DFT helps us to give an insight into understanding it. And then it also helps us to understand the CHEM theorem, which sort of like relates electrons that are non-interacting. VASP is Vienna Ab Initio Simulation Package. Vienna because it was licensed by the University of Vienna. Ab Initio because ab initio is a Latin word that means from first principles, from the beginning. Now, ab initio means from first principle because the VASP helps us to solve the Schrodinger equation from the first principles. Now, VASP helps you to do like DFT calculations, and for you to do that, you require 4 input files. I like to think of POSCA with the mind of position. INCAR sort of like tells you what to do and how to do it. It shows you like a list of calculations, and you have to figure out which one is it you want to carry out. POSCAR is potential, and K points are like sampling points. Like it helps you to figure out which points you are interested in for the particular molecule that you are dealing with. Now, we'll start with the POSCAR. POSCAR, when you think of POSCAR, you just think about coordinates, lattice geometry, X, Y, Z, that's all. Now, first of all, you generate the molecule in a Gaussian output and try to convert it into a PDB file, which is something readable by the JMO. Now, you go into JMO, you measure the length of the molecule, you delete the extra ones and save it with a .xyz extension. You want to look into that file to ensure that it's properly sorted alphabetically. Sometimes the one I have right here has been sorted. So when it's not sorted, you have to use like the sort command to arrange it alphabetically. Now you want to look into the POSCAR file to make sure that there is a space in between like the number of the atom, which is 8, and the listed number of atoms right here. After which you want to rotate the molecule and check that it has been rotated. When you check that it has been rotated, you find this list of files, the X, the YX, and the ZYX. Now you use the tin command to generate the lattice correlation. Remember that POSCAR helps you to understand just the lattice geometry, X, Y, Z, that's all. Now you want to define INCAR. Like I mentioned initially, INCAR contains parameters of the calculation. That's why, if you remember very well, when we're doing molecular dynamics, when you're defining your INCAR, it's with a different INCAR. Here, what you're trying to do, the INCAR is with geometry optimization. That's why this command has geometry optimization. With INCAR, you can do spin polarization, you can do heating, you can do molecular dynamics. You just need to specify which one exactly it is you want to do. Now, the K points sort of like helps you to pick out the sampling points, the points that you're interested in, and it contains the mesh size basically. And the accuracy of this mesh size is dependent on the number of K points. Both of the templates can be found in the bin folder. Now, POTCAR is basically potential, and it simulates interaction between the electrons and the nucleus, basically. Then, if you remember very well, this code right here, this POT_PB, apparently is just shorthand for finding the potentials of certain elements in the POTCAR. That's why you have to specifically specify C and H, because this line right here helps you to find the potential for carbon and hydrogen in the POTCAR file. So you want to check the content of the file and be sure that you have everything that you need. Then you can go ahead to run VASP. Now, after running VASP, I want to plot my orbitals. I want to make sure that I create another folder for the orbitals, because if I create the folder inside the one that contains the VASP, and it sort of like overwrites my VASP calculation. I'm going to make sure that I create another folder right beside. I have the one that has my VASP, and then the one for the orbital is right beside it. So after creating the folder, I copy all of the VASP input files and my INCAR into the new folder. Now, I'm going to check the contents and see that it has INCAR. I want to look into this INCAR. What INCAR is basically going to show me is like the Fermi energy and also the individual energy of the individual occupied and unoccupied orbital. Now, I use the grep command to just, see the number of orbitals, and then I want to edit the INCAR file. Now, I'm plotting the orbitals within a particular energy range, and I want to make sure that the energy range contains both the occupied and unoccupied. So I'm going to pick an energy range that has for occupied and unoccupied. That's why right here, I edit with the number 16, which is the number of orbitals, and here the energy interval, which is -8 and -2. Then I'll run VASP. When I'm done running VASP, it specifies this energy interval and the K points of the different orbital that I had plotted in between that energy range. I want to look into that file and make sure that I can see the per charge orbitals here. Now, the per charge orbital has it comes in a form that is not visualizable by Gaussian. So I'll convert from the ALLK to cube.pl, which is a form that Gaussian can read using the VS tools. After which I come into Gaussian, go into the folder that I have those per charge orbitals plotted, and I want to change the file type to cube. I open it up. I come here, I change the surface actions to new surfaces, and there I have my CHEM orbitals. Now, this is what I found out about the KS orbitals. I never knew why you plot the KS orbitals, but this is what I found out. When you plot an orbital free using the DFT, it tries to compute the energy of the interacting electrons. However, it's not very accurate, because the formula for the energy of an orbital free DFT has some components that are not exactly solvable. But the KS orbital is like a fictitious, it's not real, but it has an electron density that is the same thing as a real system. And the energy formula using the KS orbitals is solvable. It's actually very easy, and it's easy to compute. So yeah, why not? Like if you give me an electron density that can mimic the one of a real interactive system, don't forget that the CHEM orbitals are non-interacting electrons. So yeah, why not? And since at the end of the day, I can get total energy from computing electron density. Yeah. Thank you. That's all.
Okay, please join me in thanking Ola for a nice presentation, and the paper is open for discussion and questions. Anyone from class attendees or visitors? I have one.
Okay.
Very general. So you don't need precise in answering, just your impression. Which real-world properties of the molecules you can extract from your VASP calculations? What can you learn about real materials?
Say like the mechanical strength.
Okay, what else?
I don't know.
Can you learn about color?
Yes, you can.
Okay, can you learn about conductivity?
Yes.
How?
From like, if you have an idea of what the energy of okay, so you can get, yeah.
Okay, more questions to Loa? More questions one, more questions two, more questions three. Okay, there are no more questions. Let's thank Lola once again. So the next presenter is check my list. Yes, Lina Alhalhuli. I'm and
yes.
So
but it's not how in Arabic it's different.
So how to pronounce your last name?
Yeah, in Arabic it's Al Halhuli. It's Al Halhuli is okay.
Okay. So the presentation by Lina is very on very challenging subject that deals with periodic solids. So to those who plan to describe solids or conjugated polymers, it is a critically important material. So virtual floor is yours. Let's go ahead.
Okay, thank you. So today I'm talking about the periodic potentials, momentum, effective mass, role of K-points, and dispersion. So I'll start with periodic potential, and then we will see the relation between these topics. Periodic potentials. So now let's start by, as we build the molecular models in the lab, and recently we tried to build a repeated units of some materials, and these repeated units can be considered as infinite repeated units, like the crystal structure. And because of that, if we look to the crystal, we see like these stationary ions. We suppose that the ions are stationary for this model, and these ions will influence the electrons, the moving electrons, as the periodic potential. So we call it periodic potential, and we have here, as we know, like the distance between this regular structure of ions in the crystal. So we have the distance between each ion is fixed. So depending on that, we apply the periodic potential that we suppose for this model in Schrödinger equation. And the solution of the Schrödinger equation in this case, as Bloch's theorem suggested, it gives us a solution as in the first in this equation, equation phi sub nk in terms of position, and the solution was as a plane wave times a periodic function. So the plane wave is represented as the exponential term here, and it's related to the as a description for the moving electron through the crystal, and it's related always to the wave vector of the electron motion or electron state, and it's multiplied by the periodic function u, which is also indicating the periodicity through the crystal. So this is the idea beyond the periodic potentials and why we apply the periodic potential in our model to solve the Schrödinger equation, and we get this solution as a description for the electron. But also we can do more, like describe the electron using different parameters. So the second one is momentum, and I'll start by talking about starting from the beginning. I mean, if the electron is influenced by a force in the system, so we can present the energy that gained by that electron as the force times the displacement. We can just rearrange the variables and get this, and from here I will go to just remind you that from Newton's second law, so in the classical mechanics or in the observable worlds, we know that we rely on Newton's laws. So just to remind you, Newton's second law tells us that the force is the mass times acceleration, and if you just replace the acceleration by the velocity divided by, or the change of velocity with respect to time, so just take the mass times the velocity, and it would be how the momentum changed with respect to time, another form of the force. And here's another relation. So I will compare between the classical mechanics for the force relation and what we have in our model as we expect that, or we deal with the electron depending on the quantum mechanics format. So here, if we just try to understand how the electron move in the crystal, we know that depending on the force, so the force, it depends, or if we increase the force, the wave vector of the electron will increase. So there is a linear proportionality between the force and the wave vector. As we said before, the motion of the electron is related, or the plane wave of the electron, it's related to the wave vector of that wave. So if we compare the classical and quantum mechanical relations, we just remembering that the momentum in the quantum mechanics, so we just can consider that the looks like the momentum in the classical object. So we know like the momentum increased by increasing the force. So here we have this similar situation. The wave vector will increase as increasing the force. So we can replace it as just similarity, and we consider that the particle in our model or in our system has a momentum, looks like momentum in the classical world, but we call it crystal momentum. And it's just was because of the electron, if you remember, that has a wave particle duality. It behaves as particle or wave depending on its state or the conditions. So this is how we just define the crystal momentum. It's Planck's constant times wave vector. So here we have another thing to talk about. It's the effective mass, and to reach you, like to understand how we define the effective mass, or what is the effective mass, I will start also from the velocity, relying on the same description here. So just remember the last equation, derivative of wave vector with respect to time, it's the force. So here, the velocity, as we know, is how the displacement change with respect to time, and just substitute that from previous relation, we will get this definition with respect to the wave vector. And this velocity called group velocity for the electron in our system. And go beyond that for the acceleration, just substituting in terms of the energy and the wave vector, and the equation would be in that form. But as we know, like using that formula that I just mentioned, and just rearrange the parameters and substitute the acceleration from this equation with the force relation, we get this form. So this form now, it has acceleration, it has force. So if we compare to the form of force from the Newton's second law, we see that this term here, beside the force, is can be like replaced by the mass, but it's not as the inertial mass, because now the mass is it's proportional to the wave vector. So that means that the effective mass varies depending on the wave vector, or on the plane wave, and that means like it's changing after it's exposed to force, for example. So this is the effective mass, and it can be changed in the system, and it's different depending on the force applied to the electron. Okay, so now let's move to the key points file. I have to explain. I need to explain now what's the role of key points and what's the relation between the key points file in our modeling with all the theoretical explanation that we have. First, we said because the periodic structure of the crystals, so we have the momentum may have many possible energies. So this is the key. So because of that, we need to demonstrate all possible energies and momenta, and we need the band structure calculations. But how key points file will help us to calculate the band structure. Before that, I just want to mention that band structure properties, it's the importance of the band structure calculations. It can determine the conductivity of materials, like wood, if it's insulator or semiconductor or conductor. And then if we correlate the between the wave vector and the energy, we got the relation called dispersion. So now we got the relation that can give us all of the information that we have so far. Okay, so just to summarize, key points file used to calculate the band structure, and it contains information to create the key points grid. As we said, we have for the momentum value, we can have many possible energies. So it's important because of that. And this just reminding for the solution of the Schrödinger equation, it has the key values. So I will just present the model that we used in the lab, the TI408 molecule. And now if we want to, we need to adjust the key points to make it like more values for the momentum, and the directions that depending on the mesh that we want to design for depending on our model or molecule, of course. So So after we adjusting the number of key points, we can run the VASP, and after that we get from INCAR file, we can see that for each key point, we have the energy, and we have more than one key point. For this model, we put, for example, 8 key points, and I just put these representative energies for the HOMO and LOMO orbitals. So I want just to show you, like, for each key point, we have for the same orbital different energy. So then, how to extract the band structure out of VASP output? We can use several commands that just to give us to forward us directly to the values of momentum, valence band, conduction band, or if you want to merge into the band. Okay. Here for to see, like, in the band what the values of momentum, valence band energies, the conduction band. So we have everything ready to plot. Then we can just use these commands to plot, and we can get the dispersion relation. As we said, it's correlates between the wave vector values with the energies. And here we can see, like I just mentioned these three because I put them in the representative values before. And if you can see, like, at each value of the momentum on the momentum axis, we can get, like, for example, here we have two energy value, one on the HOMO and one on LOMO orbital. Okay, so for the another model, I just tried to calculate the band structure, and I get this shape. It's weird, I know, but depending on my model, I get this. So it's showing also the dispersion relation, and that's it. Thank you.
Okay, please join me in thanking Lina. So, any questions? Anyone who plans to do calculations on conjugated polymers may resolve confusions by asking her. Okay, I plan to do calculations, so I will ask. So, can you flip back a couple of slides? Yes, one more.
One more.
Yeah, here. So, based on this image, which particle has larger effective mass, electron or hole?
So I guess it would be the electron. No, it would be the hole, because it's moving slower than the electron.
Okay, so the shallower curvature gives larger mass. Excellent, excellent. Yes.
Yeah, because electrons and holes, we can, right.
Okay. And is it possible to apply concept of effective mass to your next to your dispersion on the next image?
Here. This?
Yes. Is it possible to apply concept of effective mass here? Or if it is challenging, why? Does it look like parabola?
It confused me already.
No. Does
the image?
Do these lines look like parabolas?
Okay.
No, correct?
Yeah, no.
And effective mass is applicable if dispersion looks like a parabola. If energy proportional to momentum squared.
Yeah, because it's proportional to the second. Yeah, second exponential. Not exponential.
Second derivative of energy. Yes.
Second derivative of with respect to k. Right?
Yes. Yes. And I want to ask one more question, but it is not to Lina. It is on behalf of Lina to the next speaker. Is it possible to compute absorption spectrum out of calculation with distribution of k-point, of distribution of momentum, and how the shape of the spectrum will change if momentum points are included. So
that's actually a question I had myself.
No, you will answer it in 10 minutes.
Okay.
Maybe Lina, you'll help Boston later. But more questions to Lina 1, more questions to Lina 2, more questions, no questions to Lina 3. Let's thank her once again. Yep. So next presenter is Boston. Hifford. Please share slides. So his presentation is on the is answer on the question to Lola. Like, is it possible to determine the color of a material from calculations?
There we go. I was trying to unmute myself. Yeah, so my presentation is on VASP and specifically light to matter interactions in VASP, because materials dealing with or interacting with light is a big subject in many different fields for many different reasons. So just a very brief overview of some kinds of interactions you can have between light and matter. Is a photon can excite an electron in the material and excite it to a higher state, or vice versa. An excited electron can be dropped down to an unexcited state and emit a photon. And there is a measure of how likely an electron is going to be excited to another state, and that is called the oscillator strength, and you can see that equation down here. That is, again, the measure of the probability of absorption or emission of electromagnetic radiation in between two different energy levels. So in order to calculate these things with VASP, you're going to need your typical VASP input files. You need your INCAR, your KPOINTS, your PODCAR, and POSCAR, and those should all be different depending on what system you're using and how accurate you want that system. So typically, again, you can change things like your precision in your INCAR file from low to high in order to increase your precision. But one of the many things you need to make sure in your INCAR file is that you have L wave equal true in order to correctly, or in order to get correct output files. And so after you run your VASP input using these files, you'll then need to create the spectrum. So as we talked about before with the last presentation, you'll end up with in your INCAR file a list of different momentums and in your K-point values. And you can see that on the right here. This was just with one K-point grid, so it's only one. And so what you're going to want to do then is you're going to take those K-points and you're going to put them into their own separate file, and you can call that file energy pop. And then you're also going to want to take the number of different bands and create a file called input overlap, starting at 1 and then going all the way up to however many orbitals there are. And then
sorry for
yes.
interrupting. I think you mean orbital energies rather than K-point values, right?
I believe so. Which one? Yeah, I might have said that wrong. I'm sorry.
For those who will watch the recordings, it may create confusion. So
okay, yeah, sorry.
Just orbitals. Okay.
So yeah, and then that last value, that's just you're gonna leave that as a 1, just because that's how the code was written. It's kind of just a dummy value there. And then after you do that, you're going to want to create the spectra. You're going to create a file called OS strength. And in order to do that, you're going to have to run the command given down there, which is going to use those two files we just created, the energy pop and the input overlap. And then after you run that command, you're going to get a file called OS strength. It's going to contain all this information that's shown here on the right. I'm not going to go through all of them, but some of the important different values that in this file that you have. On the very far left, you have the index of the occupied orbital that you're starting with. And then your second column, that is going to be the orbital that you are transitioning to. And then the third column, that is the oscillator strength, which I had just mentioned earlier, which it's essentially a measure of the probability or of the likelihood a transition can happen. And then the fourth column is the energy of that transition. And then the second column is the number of the next column is the number of electrons in an occupied orbital. And then finally, it's the number of electrons in an unoccupied orbital. So this is the information that you're going to need in order to create your spectrum. And what you're going to want to do from there is with your OS strength, in order to create the spectrum, you're going to want to run the command bin spectrum _ IMP3. And you're going to need to enter the necessary information. So I've got them all boxed out so it's easy to follow along, but you're going to need the number of transitions that are in OS strength. Then you're going to need to set the minimum and maximum energy, and you're not going to want to set the min energy to 0 because in the code there is a division by the min energy, so if you don't want to have a division by 0 in there. You're going to want to set the width of each line, and that's in electron volts, and then you're going to want to set the number of the HOMO in the file. And this will result in a file called spectrum, and the file spectrum contains all the necessary information that you're going to need to plot your spectrum. From this, you can use whatever plotting tool you want. You could go and plot this in Excel or something else if you have it. There are some pre-made commands that we can use to kind of speed up the process a little bit, which we'll talk about. Before we get to that, I want to just mention the spectrum file, which you see on the right, contains 4 columns. So it's going to contain the wavelength of the transition in nanometers, the energy in that of the transition. Those two are interchangeable. So wavelength can be interchanged to energy and vice versa. And then the third column, that is going to be just the normalized transition intensity. So it's going to just go from 0 to 1, being the max. Whereas the far right column, the fourth column, that is going to be the transition energy, but not normalized. So typically you use the normalized one just to go from 0 to 1. That's pretty standard practice. But as I said, using those 2 commands down below, we can plot the spectrum against either electron volts or against wavelength. You might want one sometime and another the other time, or both. But you can use those 2 commands down there. And then that will create some PS files. And then all you need to do is use PS2 PDF WR to convert those PDF files those PS files to PDF files. And then you will end up with spectrums such as down below. Now, this process that I have been talking about has been for unspin polarized and just for singlets. However, these can get a lot more involved. So if you want to do singlets or doublets, triplets, which just refer to how the electrons are paired in the atom or molecule, you can do that in VASP. And really all you need to do is you need to set I spin equal to 2. That tells VASP I want to do a spin polarized calculation. And then you want to change N up, down to either 0, 1, or 2, depending on which system you want to do, which will be singlets, doublets, or triplets. And then in order to create the spin polarized spectra, it's a very similar process to what we just did before. You're going to want to end up having a file called OS strength, but instead of just using that initial command we talked about before, you're going to want to use these 2 commands that create the OS strengths for transition between orbitals with spin up electrons, and then you want to do one for transitions between orbitals with spin down electrons. You're going to get 2 separate files. You're just going to want to rename those OS up and OS down respectively. You want to delete the original OS strength because we're going to create a new one where we combine both of these 2 files into one, so it makes it easier to plot. And then you're just going to plot it in essentially the same way that we just got done plotting before. So you will end up with different spectrum depending on, again, how you set up your system. And so that's pretty much it. Thank you for listening.
Okay. Yeah, please join me thanking Boston. And any questions are welcome.
I have a question, please.
Oh,
Yep.
please.
Can you go back like 4 slides backwards?
Say where to?
Can you go like 4 slides backwards?
4? Yeah. 1, 2. This one?
The next one.
This one?
Yes.
Mm-hmm.
What's the difference between the normalized transition intensity and this transition intensity? Because like I see the numbers are, they're the same thing. So.
Oh yeah. So the spectrum file is really huge. So right now, all the ones that I'm showing, this was just the head of the file, and these are all going to be 0, just because that's the value, and you're not going to be able to if you normalize 0, it's just going to stay 0. But if you were to scroll down, you would see some values, they jump up to like in the hundreds or thousands on the far right column, whereas the ones in the third column, those stay under 1. And that's, again, just to normalize things, because you want to often keep things normalized. And the way you do that is essentially you're just taking the highest value of the transition intensity and dividing every single value in that column by that highest value. And so that'll normalize everything from between 0 to 1. And that just gives you a better depiction because this is you want to compare spectrum to others sometimes, and sometimes those spectrums will not be comparable if you leave them unnormalized. They'll just be huge in one sense and then tiny in the other, and so it'll be very difficult to tell what's kind of going on. Whereas if you normalize that, all your spectrum will be relatively. You can see the relative intensities in them that way.
Okay.
So
thank you.
Mm-hmm.
More questions? I have a couple.
Yes.
Slide number 9.
9. Yep.
Last image. If you present this slide set once again, put second arrow up on the next level. This next last, the rightmost.
Oh yeah.
This image prompts violation of Pauli principle.
Yep. I should have double checked that before I took the picture from somewhere. My bad.
Okay, so question on behalf of Lola once again. So how to learn about color of material based on your calculations?
Yeah.
And after answering this, also tell what is the color of material with a spectrum on slides 8 and 11.
Yeah. So
general first, and then particular second.
Yeah. So the way you can tell the color of a material based on the spectrum is if you are shining white light on it, which contains all the colors of the rainbow, the colors that are more heavily absorbed won't be reflected off of that material. So like, let's just say the material reflects all colors except for green, absorbs all colors except for green. That means green will be reflected and the material will appear green to us. Now you can use the spectrum like this and you can see which colors are more or absorbed more intensely than others. Like, so for example, the color here at around 370 some nanometers is much more strongly absorbed than something around 300 nanometers. And so that means anything shining on this material that's at about 300 nanometers will get reflected rather than absorbed. And so I always forget the ranges of the colors for nanometers, but I'm pretty sure that it's between roughly 400 and 700 is the visible range of the spectrum. So right now it's looking like this would be like a white material, although I'm not even sure if I'm actually plotting all the way up to 700 here. But assuming that it's just dropping down to 0 there, it would be a white material.
Okay, perfect. This is white material, titanium dioxide. If you have saw it, it is a white powder, and it is used in cosmetics for sunscreen. So it is a white cream that one applies to the skin. Slide 11.
Yep, slide 11.
What's the color?
Oh, yeah. So the color for this one, so again, visible wavelengths are roughly between 400, 700. So, and then 400 would be towards the bluer end. So this would be a bluish color. Then, or excuse me, this would be a redder color because blue is getting absorbed and red is being reflected more. You'd have some greens in there as well, but
since it is a broader spectrum, it will be like maybe even brownish or blackish.
Yeah.
So for bright colors, it should be either a bright peak or bright gap between peaks. Oh, does it make sense? Okay.
Yeah, it does.
Okay. Yeah. More questions to Boston? We'll leave for later discussion the momentum dispersion, but it is very similar to how you computed spin polarized. You just partial contribution from each value of momentum and then add them together, and overall line is broader. Okay, please join me thanking Boston. So next presenter is Sarah.
Yes.
And the Sarah Gazenpalo.
Yes.
So virtual floor is yours, and the things she all materials presented today are important for the project, but it's quite important for the projects what she presents.
Yeah, thank you. Hello, everybody. Today I'm going to talk about modified electronic configuration, including anion, cation, excitation, and then the unrestricted DFT, including the triplet orbitals, and their density of states images. Here are some schematic figures for the neutral state or ground state in the left, and then n-type doping on the right. As you can see, for the neutral state, these are the energy levels for and you can see the HOMO and LUMO, and then absorption spectra on the right. For the n-type doping, which here stands for the negative, it means that we insert 2 more electrons to the model, so we call it anion. So, and you can see the absorption spectra on the right as well. You can see that the HOMO and LUMO changed here. So the other one is called the p-type doping, which means we withdraw 2 electrons from the model, so we make it positive or cation, and you can see again the absorption spectra as well. You can see that the HOMO and LUMO change, and we have another HOMO and LUMO. And these are the absorption spectra, and then the energy levels for the conjugated polymer. And here is the another schematic figure for the spin polarization. It's kind of the excitation and the optimized geometry before and after excitation are shown as well. So I'm going to explain how to plot their density of states in the following slides. Here for the cis polyactylene model, for the neutral states, one thing that you should figure out at first is the number of electrons. So you can use grep number of electron outcar command to see how many electrons we have in the neutral states. And you can see that in the right, the number of bands and the HOMO and LUMO. So we create 3 subdirectory called anion, cation, and excited. For the anion state, at first we copy postcard, PODCAR, KPOINTS, and INCAR files from the neutral state directory, and then we are going to edit the INCAR file and insert the number of electron equal to 42. 42 means 40, the number of electrons for the neutral states, plus 2 for make it anion. And then
after saving the INCAR file, we run VASP. For plotting the density of states, we copy band energy information from INCAR file into the new file called states, and then we execute this command bin dress dose norm, and then use gnuplot to create the PS file, and then use the last comment. Use the last comment to convert the PS file to the PDF file. So in the right, you can see the density of states for the neutral, and then in the below for the anion state. You can see that for the anion state, we have more electrons, so we injected 2 more electrons to the model. For cation state, we have the same process as anion. However, for the INCAR file, we should decrease the number of electrons. So in this case, I decreased number of electrons from 40 to 38 to make it cation. And after saving the INCAR file, again, we run VASP and use the same process for, as I explained, for the anion state, and plot the density of states for the cation. You can see the neutral and the cation density of states and the top and below, and you can see that for the cation we have less number of occupied orbital. For the excited state, at first we should know the number of bands, so we easily use grab number of bands or NBA outcar and see how many bands we have for the neutral state. And then in this excited subdirectory, we should copy a postcard, and the key points file from neutral subdirectory, and then use this command to copy the INCAR file. And then we should edit the INCAR file using this command fervi. And here you can say, for example, from this model, I said that I wanna the first 19 orbitals be occupied, and then the next orbital I wanna be empty, and then the next one, which is 21, I wanna be occupied, and then the rest I wanna be empty. After saving the INCAR file, we run VASP, and then use the same process for plotting density of state. As you can see in the INCAR file, you can see that the first 19 orbitals are occupied, and then the orbital number 20 is empty, and then the 21 is occupied. And you can see the density of states for this model on the right. For the triplet state, after copying INCAR, postcard, podcast, key point files from neutral states directory, we should edit the INCAR file as well. Use is spin equal to 2 for spin components alpha and beta, and to say that we wanna have a spin polarization calculation, and up and down equal to 2 for the triplet state. And if you want to have the singlet, you use 0, and for doublet you use 1. So after saving the INCAR file, you're going to run VASP, and here after you executing more INCAR, or to see the INCAR file, you can see that you have 2 components, for one for the alpha spin and one for the beta spin. So here in this state, we create 2 states file, calling states up and states down, and saving these bands information into these 2 files, and then execute dress those up and those down for the states up and state down. and use GNU plot this command to create one PS file. And after creating the PS file, we are going to convert it to the PDF format, and then save your PDF file in the local computer. And you can see here the density of states for the triplet state, and you can see that some electrons from HOMO are transferred to the LUMO. So this is kind of the excitation. So how to plot the orbitals for triplet states? After creating another directory called orbital and copying PodCar key points wave car from triplet state directory, we should copy the CONTCAR as a postcar in this directory. After that, we execute this command to create the INCAR file, or copy the INCAR file here. And then in the INCAR file, you should mention number of bands. Here in this model, there are 40 bands, and then you should say I spin equal to 2 for spin polarization, and then minimum and maximum energy also we should mention it here. After inserting this information into the INCAR file and saving it, we are going to run VASP. So after running VASP, you can see that there are some partial charge file in the directory created by VASP. So you are going to save that partial charge files into the local computer and open the VMD. After opening the VMD, you are going to open a postcard in the VMD and add the partial charge file to that molecule. So for showing as you can see in the right, for showing the different orbitals, you have 4 options: spin up, plus, down, spin up, minus, down, spin up, spin down. Here I'm going to show you the orbital for the spin up and down. So I select the 3rd option. So you can see in the left the HOMO spin up orbitals, and then the HOMO spin down orbitals on the right. Thank you for your attention.
Please join me thanking Sarah. So it is very dense talk. If we would have a bigger class, it would be split on maybe 3 shorter talks. So any questions? And I think Kia may want to ask this subject because she was originally preparing to talk about it. Did you catch Sarah in telling something wrong, or you have some questions? No? Okay.
Is that a question? Sorry.
Please, please.
Sure. Sarah, this slide, what's the difference physically? Aside the white color on like the red for the spin-up orbitals, like what's the difference physically?
These are the orbitals plot for the spin up and spin down of the LUMO state for the titanium model. As you can see, their shape is completely different from each other. I don't have a kind of exact response for you. These are the cloud of the orbitals for spin up and spin down. You can easily adjust how the size of these clouds for the spin in the VMD. There are some details for kind of adjusting these orbital size and then the shape. These are the orbital shapes I faced in the VMD.
Yeah, I wasn't seeing it properly before, but yeah, but now I can see it. Thank you.
No. Let's discuss it. And the question is very, very deep. So Lola has a very good eye and curiosity to ask about it, and the question deals with chemical intuition of a professional chemist. Maybe you have it on the background, and also to all of us who took chemistry in at least high school. So please share opinions. What you, if anyone does see a difference. There is a drastic difference.
Of course, the shape of the orbital is completely different from each other.
It's not completely, but if we would look along x-axis,
orientation maybe of the.
so do you see what I'm showing, or maybe if
yeah, the orientation of the orbitals.
Exactly, and who is aware of the importance of this orientation? What does it change?
Mm-hmm.
So look here, and if you are if you will be comfortable with this image, you will immediately pass inorganic chemistry class. So if the orientation, if the petals, so to say, if the clouds go between anion oxygens, if this between, then interaction between electronic clouds of titanium and anion ligand is less. If they are coming literally, if they overlap these clouds of titanium orbitals and positions of the negatively charged oxygen, the interaction is much stronger, and it depends on the values of energies. So this orientation of the orbital, so it's they both are d orbitals on titanium, but they are shifted in space by 45 degrees, and it does change type of interaction. So the difference is not negligible. Mm-hmm. Thank you, Lola. Thank you, Lola, for good eye, and it's what a professional scientist does. Identifies little differences. Excellent. More questions? I have a couple.
Yeah, sure.
So the question is not smart. It's a technical. In your example for excited state,
mm-hmm.
or Fermi, and let yeah, please come there. Yeah, no, before, and yeah, here. The keyword in the box, and let me attract attention of everyone to this slide, because it was not shown in the labs, so it is the first time when the rest of the class is seeing it. In this Fermi weight equals 19 times 1, 0, 1, 8 times 0, you are flipping occupation of HOMO and LUMO. You are promoting population from orbital HOMO to orbital LUMO. But is it mandatory to promote only from HOMO to LUMO, or one can, if needed, promote from lower lying occupied to higher lying unoccupied?
I haven't tried that.
Just
but
but you
but
don't. Yes, I'm listening.
But I think it's not possible. We should kind of excite the model from HOMO to LUMO, or the highest occupied orbital.
No. You can excite it as far as you want, because it models the molecule under photoexcitation. If we excite the system with higher energy photon, with shorter wavelengths, it will promote different electrons, and it could be a practical thing for a couple of projects. I keep Lola, please focus on it. In your project, it likely will be a part of calculations. Whew. More questions to Sarah? 1, 2, 3. No questions. Let's thank Sarah once again.
Thank you.
And last in the sequence, but not least in importance, is presentation of the full name is Kamrum Nahar Kea. So she will cover a very important skill and material about exploring materials at ambient temperatures. Everything we did before Kea was dealing with molecules and materials at 0 Kelvin, absolutely frozen. And Kea helps us to go to warm up our consideration, to look at materials which are at room temperature or maybe higher. Okay,
So,
Kea, virtual
yeah.
floor is yours.
Thank you, Professor. Are you able to see the slide? Yeah. So today I'm talking about these three topics, and for the most important part, I think this one. I like this one too much. That the above two one also good, but this three movie based on molecular dynamics, that one is too good. Okay, so let me, yeah. So for the molecular dynamic at room temperature, what we need to do, because Lola, she already told us that how to build a model. We need to use VASP or other software. And suppose we build a model in a VASP, then we need to follow the step already showed by Lola. Then we need to copy we need to make a new directory for conducting this things, molecular dynamic part. So for this, I copied the INCAR, postcard, KPOINT, and the podcast file. So here the most important part is the INCAR file. So in the INCAR file, we are able to see that there is the term like in IBRI in I BRIO. This one actually determines the ions are updated and moved. This one is zero. That means actually when we conduct when we will calculate the molecular dynamics and perform the molecular dynamics calculation in the VASP, then we use that IBR ion 0. And actually this one is used to relax the whole model system, especially the local energy minimum. And for like if we if there is an ion -1, the value of that one is -1, then there is no update. If you want to calculate another things like ionic relaxation or conjugated radiant algorithm, then you need to change the value of this. So here, because we want to do the molecular dynamic calculation, that's why here I didn't change anything. And this one actually related to NSW, and that NSW actually gives the NSW. It's here we use 30. NSW gives the number of steps in the molecular dynamics round. Since when we run the whole things in the valves, it gives the steps of the molecular dynamics. So there are another things. It's like TEBEG. It's 300, and there TEN 10 300. Actually, this one used when we like to set up our systems into like an equilibrium position. that one I didn't change anything from in this section. I just changed in there because I want to run this model quickly. If I didn't, if suppose there was I guess 300, if I didn't change anything like 300, then it will be it will after the end of the result, when I want to plot a temperature graph, then it will show some equilibrium condition, but now it will not. So 10 is sets the final temperature of the molecular dynamic when we run that one using uh, I, IBR ion and 0 and smash equal to there we use -3. So let's go to the next step. And after oh sorry so when after changing the NSW here 30, then to submit our job. So here I use the photon. So you need to use this command. If you want to use the nurse, you need to go into log into that site, and you need to submit using this one q sub and this. After that you need to wait for that. Okay, so after finishing the job, you will able to see the heating is and temperature you will able to see from there in the concar file. And after that, if you want to see that how temperature depends on time, so here it's not a time. So temperature actually depends on when we I open Zikr file, it will show that it's there is for like a temperature. This one is energy. So I guess it's farm energy and initial energy and potential energy, those. So if you want to see the if you want to track the temperature, so you need to follow this command, and after that so when you will get this one uh, tt.ps file, you need to use the I didn't wrote here. It's we all know that one PSP PDF PDF WR WR this command to convert that one into PDF file. So here I plot the graph for this one for the temperature. It's it will not show the equilibrium state because I already said that because I changed the NSW 30, that's why it shows like sine curve. But if I suppose if I will work on the nurse, it will be able to we will able to see the equilibrium state there. So there is another way to track the temperature in the molecular dynamics situation. So suppose before before developing that the PDF file, you can check your result in the photon. So you need to follow these ones and follow these steps like gun plot and this. Then after that suppose you want to plot for tt3wl, you will able to say this one. I'm trying to plot for the several graphs for 3, 5, 7 to see how they actually uh, um, I I still I didn't get that. I have a question for professor actually. So why this graph? The meaning of the graph that I will ask him later. And after that, the thing is this is the most important things that I like this one. So INCAR file is almost same. I didn't change anything. So these are the most important part in the molecular dynamic. We all know that. And we already did the molecular dynamic in calculation in the VASP using photo server. So after that, we need to I download the outcome file, and here I use VMD file, VMD software to open in this one. So for the professor already showed these steps in our class. So suppose you need to like new molecule, and then you need to browse from where you download it. Then you need to load that one. So see, after loading your output file, you will able to see a number of atoms and number of frames there. So after that, you need to adjust the molecule. So here is like a graphics. It's written here. So if you click the graphics, you'll able to see several options. So I choose a graphical representation because I want to adjust the molecule. So first I choose dynamic bonds, and then later on I choose CPK, this one, and I also change the color. And here, when you use the VMD software, you will able to see that there is like a black, sorry, black background. So I prefer the white one. So if you want to change the background of the this, so there also there is option for graphics. If you choose that one, you can change the color of the background too. For the like if you want to publish any paper, this is good to use the white background. And I think this is okay. So for adjust the setting, what you need to if you want to make a movie, so what you need to do, go to the extension visualization movie maker, just click that. When you click the movie maker, there is one windows will be appear like this, and you need to set something like that. In a movie setting, you need to click trajectory file, and obviously you need to uncheck the delete images file, because we want to using when you click make movie, you need images, because using that images that software will create a movie. That's why you need to uncheck that one. In the format section, you can choose this one or the mpeg one, that one too. So after that, here you need to set a directory where you want to save that movie, and also you can change the name of the movie, and obviously if you want, you can change the movie duration. So after that, if you click make movie, then you will able to see the movie already made. So there I just show that there I choose this FFmpeg, that one. I also try for this one, ppm, this one, and I also able to create the model using this. So for this one, you need to choose sorry, you need to uh, you need to write this command in the terminal. And after that, like this one, I plot only, and there are several frames there, 20 30 frames there. So I plot this one for the 13, only 13 frame, number of 13 frames. And so that FFmpeg, you need to download that software, and this one for the Mac actually. So you need to download that software, and after that you need to install that one using in a terminal. So those are using a Mac. they are easily able to install that software. And after the end of the movie making, the result is like this. So this one is good for the publication, like images. I know that we use images uh, when we want to publish a paper, and for the if you want to go to any conference or and you want to see your result to others, it's better to make a movie. So that's the purpose of the movie making. That's the thing. And there, after the end of the movie making, here we all obviously we all know that how to upload that those movies. If you want to upload movies in YouTube, you need to follow these steps, and you need to sign up from your using your Gmail account, and there will be and there you will able to see the this kind of option, like there is a upload option. You need to upload that one, and you need to set some privacy. After that, if you want to publish that video, upload that video, you can upload that video using the following steps. And okay, so I did that one. I upload that one to just for checking. And this one is, suppose DMD, you can, it's not like that you can make a movie using DMD in a Mac. It's not like that. You can, I did it using INCAR file. If you want, you can use the XDAT, XDAT car file, concar file, and postcar file too for making a movie. And in Windows, you need to install another software because it's different from the Mac. So that software name is Video Mac actually. So there is a link for that one, and there is another option for making a movie. It's JMOL and Avogadro. So we used JMOL. Professor showed us before, but not a movie making part. But if you want to use JMOL to make a movie, you can do that. And so you need to use this one. You need to convert generate XZ file from the XDAT car file, and then after that you can open that XYZ file in JMOL, and after that you can make you will able to make a movie too. Okay, what happened? Okay, so suppose if you want to learn anything about VASP and how they use that one actually manual, so you need to go in this link. Just open this one, you will able to get anything. If you have any question, anything like how to use VASP and other commands, you can go to that section. There are several tutorials and examples also there. So thank you so much. Any question?
Okay, please join me in thanking Kia. Very important and interesting, and your sense of humor. So, any questions to Kia from class attendees or visitors? So please think about your questions. I'll ask the first one.
Of course.
Thank you. So, which new research information one can learn from movies of molecular dynamics? Like if you need to sell or to advocate the skill that you presented to the rest of the class, why other class attendees need it? Which research information can be learned from movies like those you did?
So why the question is why they need movie making like this, right?
Which new scientific, which new research information can be found from molecular dynamics?
Um, from the molecular dynamics, actually, they are able to see how the molecule actually react with each other, ion type of ions,
Perfect.
then how they react with each other, the graphical representation, this kind of things. Like here, when we did heat, uh, heating and molecular dynamics, it's true. And after that, we will able to track temperature. So if you want to do the other things, I think from that we will able to do the rest of the part.
No, it's really great answer. So I can add a little bit details. Reactions in the movies that Kea did show, the interatomic distances were oscillating. But if one changes configuration, or if one takes more volatile compound, or if temperature is higher, bonds can be broken. So it could be dissociation reaction.
Yeah.
Right?
Yes.
Also, one can observe polymerization, how monomers connect into intact polymer. One can look on dynamics of adsorption and desorption. And there is one thing that Boston would appreciate. Well, so Boston did present how the partial absorption of light by alpha and beta spin add together to get overall spectrum. Then we discussed how partial absorption of light at each value of k of momentum adds together and give broader spectrum. Right? Now, next thing, one can take snapshots of structure along molecular dynamics.
Yes.
And compute absorption spectrum at each point of the dynamics.
Yeah.
Because of the oscillations of interatomic distances, energies will be a little bit smaller or a little bit bigger. And if one adds together such spectra, they will gain broadening line shape. And we were already mimicking it when you were giving a parameter of line width in density of states and in spectrum. We were artificially mimicking the process of line broadening because of thermal motion. But now, with the skill that Kea presented to us, we can compute broadening of lines from first principles. Okay, more questions?
Okay.
Any questions from Steven? No? Then I have a question to Steven. So, as a system administrator of Photon, do you know if it is installed or you plan to install VMD and FFmpeg on Photon so that we can generate movies right by logging into Photon?
I do not know if VMD is currently installed on Photon.
But is FFmpeg image processing too?
Yes, I think so.
Okay, then we can practice the command that Kea taught us right in the command line. Okay, yeah, thank you, Steven. Dr. Han, do you have any comments, questions, or suggestions to any of the attendees?
No, I'm good.
Okay, thank you. Well, last chance for questions. 1, 2, 3. No questions. But thank Kia and all speakers, all presenters, and special thanks to the special guest, Dr. Yulun Khan, who is author of several tools that were presented today. So everyone who presented gets a credit towards final grade, so that you will not regret. Congratulations on accomplishment of this stage, and starting from tomorrow in the lab, we will begin new life. We will begin your research projects. So congratulations on accomplishing this milestone, and meeting is completed.